It fits quite nicely with the previous presentation and also fit directly to the question that Joseph asked for the previous presentation. So the motivation here is that C and C++ programs use libraries via header files. And one problem here is that you can miss some information because the header file then contains the definition of the function or the declaration of the function, and the definition of the function, like what the function actually is doing, is then missing. And one way to go around here is that we can use compiler attributes to annotate the declaration to provide hints to the compiler on what the function is actually doing and how to compile the code that is calling the function. And this is especially important for memory access behavior and as MPI accesses memory, like for example, message buffer, MPI API has quite a lot of pointers to it. This problem may be specifically of interest into MPI. So I have a motivational example here. I hope you can bear with me with this assembler code here. We have a C program and it will compile into this kind of assembler code here on x86. So first we store the 42 into the variable, then we set up the argument for the function call, then we call the function. After the function may have overwritten the value because we give it the pointer to the variable, so we load back the variable again, and then we perform the addition here in line 3 of the source code. Yeah. If you tell the compiler, however, that the function foo in this example actually only reads the pointer and it will not write through the pointer, then the compiler can optimize the code and compile the code into a different code. So with information that the function foo only reads through the pointer, we still need to store the variable into memory because the function can then read it from memory. We still need to set up the call argument, then we call the function. We don't need to read back the result from the function because now we know that the function actually has no result that will be stored into the variable. And then here you also see that the compiler in this case can do some constant propagation and it will remove the need for the addition in this place. So what we implemented is, what we want to try is, the problem here is that we don't know if MPI reads or writes memory and how MPI handles memory because this information is lost when we just included it as a third-party library basically to our application. So what we want to do is that we want to annotate these informations back to the compiler so that the compiler can hopefully compile some better code. So there are a couple of LLVM attributes that we can annotate. So we annotate the attributes at the LLVM intermediate representation level before all the other optimizations are taking place, so that the compiler has then more information on what MPI is doing, and it can then generate better code. So there are a couple relevant attributes that we can utilize with MPI that are already part of LLVM. The way how it usually works is that if you have functions that are inside of the same translation units, for example, the compiler will automatically deduce the arguments because it knows about the function definition. It can then inspect the meaning of the function definition, and try to figure out if the function only reads memory, if the function only writes memory. So usually this is applied automatically. We, however, do not apply this automatically. We read the MPI standard document and deduce the relevant attributes from the standard. So what are the relevant attributes? One is the memory attribute. It specifies how the function reads or writes memory. Mostly we are seeing this memory attribute. This attribute tells us that memory is used through the arguments, and the function can read and write to memory that is given via its pointer arguments, or it can read and write to inaccessible memory. In the case of MPI, it means some memory that is then managed by the MPI implementation. The important part here, if we specify the memory argument like this, is that accessible memory cannot be modified. It cannot be read nor written by the function because either memory is read or written by dereferencing the pointer arguments, or it is we read or write, we deal with memory that is inaccessible to the current calling context anyway, and all other memory this function will not touch. And this is what this attribute here is telling us. Then there are other attributes that you can annotate to individual pointer, not the whole function, in order to tell, okay, this pointer is only read, this pointer is only written, or this pointer will not be dereferenced at all, to give a more precise description for each individual pointer. For each individual pointer, there's also the no capture attribute. Sometimes it's also called no escape. In LLVM, no capture implies no escape. This means that the pointer is not captured and does not escape the current function. Basically, what it tells you is that, okay, once the function that uses this pointer, it can read through the pointer or write through the pointer, yeah, depending on the other arguments here. Once this function call commences and returns, the pointer is basically forgotten. In terms of that the function that you've called, they will not keep track of the pointer and they will not use the pointer after the function call has been completed in order to, for example, modify some memory through that pointer. So we don't capture the pointer, often also called no escape, that the pointer does not escape the calling context of the function. So the pointer is only going to be used while the control flow is in the function that we call, and afterwards the MPI library will forget about the pointer here. And then most MPI functions can be annotated no free as well, because they don't free any memory. If we pass memory into MPI send will not free the message buffer. So we can also annotate that. So what are the relevant annotations that we can make? It looks like this in LLVM. So we declare, for example, MPI send. Then we have this no capture attribute because MPI send is a blocking operation. So the pointer will be read. It's read only. Yeah, as we do the send operation will not write to the message buffer. It will read through the message buffer pointer. And then after the operation is completed, MPI can forget about the pointer. MPI will not use the message buffer anymore because the operation has already been completed. So we can also annotate the no capture here. We note that there are some other pointer arguments, data type and communicator. We do not annotate those pointer arguments because the MPI standard does not mandate that those arguments have to be pointer argument. This is a pointer argument according to the MPI standard. Here in OpenMPI implementation, data type is also a pointer argument. If you use a different MPI implementation, MPI-CH, for example, it's an integer argument. In this case, we don't annotate those pointer types. What we also annotate for all the different ways of MPI send function is this argmem. Yeah, so we tell the function, okay, MPI send is only accessing memory directly through the pointer arguments, either through the buffer argument, which is the most important argument, or data type or communicator in this case, or it will access some inaccessible memory. This, however, may be wrong in certain situations because you can use MPI bsend with MPI buffer attach. It works like that. You attach some buffer to the MPI library, basically tell the MPI library, okay, here I have reserved you some buffer. You can use it in order to buffer some messages. And then you do MPI bsend, send the message, and some time later you can detach the buffer. In this case, we still annotate that the function actually only accesses memory directly through the arguments or some inaccessible memory that is not accessible to the current calling context. Because the reason here is that basically, if you read the MPI standard, you are not allowed to access the buffer at any point here because you basically tell the MPI library with MPI buffer attached, okay, please manage that memory for me, and I need to explicitly detach that before I can use it again. So therefore, technically, this is wrong. MPI bsend can modify some memory that is visible in the current caller's context, namely the buffer. Yeah, but if this leads to any problem, because here the buffer is used, this is undefined behavior according to the MPI standard anyway. So in this case, what we are telling the compiler is, okay, if it is undefined behavior according to the MPI standard, you can treat it as undefined behavior and do whatever you like. For the usual, if you don't use the blocking send operation, then it is clear that MPI send will only access memory directly through the argument, so the message buffer, or some other memory that is not visible into the current caller's context because it is managed by MPI anyway. For a non-blocking communication operation, we can actually attribute the non-blocking operation exactly the same as the blocking operation. Okay, so we also and annotate the request object, but importantly, we can also attribute the no capture attribute to the buffer, which again is technically not correct because the isend operation, what it does is it reads the message buffer and then it somewhere will store the message buffer away and then the network device can progress the communication in the background. Yeah, we have a non-blocking operation. But what we can tell the compiler here is actually MPI is finished using the buffer after the ISEND has commanded. And the reason here is again the same. Yeah, so the no capture reflects the semantic of the standard because the user is not allowed to access the buffer anyway before the operation is completed, before they ensured completion, for example, with MPI wait. So this way we tell the compiler that, okay, it's completed at that point because we know that it will not trigger undefined behavior, or at least no undefined behavior that wasn't originally in the application. Because at the point of the MPI send, the compiler now thinks that the operation has completed, and we know that this will not be a problem because before using the message buffer in any way, the user must ensure completion, and then telling the compiler that the operation has been completed is the correct thing to do. And this is also a thing that the compiler by itself, if we assume that the compiler should perform this annotation here, the compiler will not figure out the no capture attribute because technically speaking, it is wrong. If you only have a look at this function here, the pointer is captured. Yeah, because MPI is going to use that pointer to read the memory, the message buffer while the operation is in progress. But we can tell the compiler, okay, you can treat the operation that it have been completed because it will be completed before any other access to the memory anyway. And so here we can annotate additional arguments to the MPI function that the compiler all by itself would not be able to deduce if it just looks at the source code of the MPI implementation itself. We can annotate all the other MPI functions accordingly. We have annotated the most important MPI functions. So we annotated the send receive operation and the collective operations. Basically, we have not annotated all MPI functions so far. For example, creation of data types or communicators are not as frequently used as collective operations. Therefore, we only started with annotating the most important MPI functions. So we tested with the exascale proxy application, with some exascale proxy application. And here you see in the figure that most of the MPI calls for most of the mini apps that we tested were actually annotated. So the question now is, okay, what does it have an effect? Does it influence the code generation of those mini apps? So there are some differences in assembly instruction count, meaning that there are differences in the assembly code. I will show you an example in a minute. There are some examples where the additional introduction of these attributes leads to less assembly instruction, and sometimes it leads to more assembly instruction. I will now showcase some examples where the compiler can trigger now additional optimizations that are not possible without the introduction of the attributes. So an example would be the removal of some memory accesses. Again, the things happen on assembly level, so we have to look at the assembly code. On the left-hand side, there are no attributes to the MPI function, which is like what the compiler normally is doing. On the right side, we have annotated the MPI functions. In this case, the MPI com size and MPI com rank are the relevant functions that we have annotated, and the relevant attribute for this is the no capture attribute. So what's happening here is, okay, we set up the function call for MPI com size, and we set up the function call for MPI com rank. At some point later, we load the size of the communicator and the rank, perform some other call called the command line options. And then here we see, again, a move instruction, we need to reload the rank pointer again, the rank variable again. And also we need to reload size again from memory. On the right-hand side, you see that this reload of size and rank after this parse command line option function is not happening anymore. Because here we need to store it into a different register so that the register will not be overwritten by the function called here. And then we can just reuse a register for the size here. We see that the compiler now removes some basically unnecessary memory accesses. And the reason why this is happening is that MPI com size and MPI com rank, we know if we have a look at the MPI standard that if you call com size or com rank, it will tell you the current rank of the process in the given communicator, and this value will not change anymore if you use the same communicator. But the compiler does not know that. Maybe the MPI implementation counts the number of messages sent in the rank variable here, and therefore the rank variable needs to be updated and read in back from memory every time. Yeah, because maybe this other function, parse command line options, that has nothing to do with MPI, maybe it will modify the value here. Yeah, the compiler does not know about that. So then if we tell the compiler, okay, we give it a pointer here, but the MPI library will only use this pointer while the MPI com_size call is in progress, and afterwards we'll forget about the pointer. This is what the no capture attributes does. We need to load the pointer one time, but then after we have initially loaded the pointer, yeah, we can remove those memory accesses, and in this case, yeah, use some registers directly instead. So this can actually trigger a bit more involved case. Yeah, this may be a bit more, yeah, it is a bit more involved and maybe a bit, yeah, esoteric. Nonetheless, I find it very interesting that what's happening here is that the compiler is able to basically replace an indirect call with a direct call just because we have annotated some MPI function. So what is going here? What's going on here? We have this loop here, and this loop basically loops through member functions. So we have this field data array, and the field data arrays contains function pointers to the member function of this domain object. And then we call this member function. The member function then itself returns a pointer that we're going to store something into. The field data array is yeah, initialized somewhere here, and it will not change anymore. So in theory, the compiler should be able to first unroll the loop, because the number here are known statically at compile time. This also happens whether or not you introduce MPI argument, the annotations. The compiler is able to unroll the loop, but then the compiler is not able to replace the indirect access here, the indirect function call here, with a direct function call. And the reason here is the MPI wait, actually. Because the MPI wait, we need to tell the compiler that MPI wait will not modify any memory that is accessible other than the memory directly given through via the pointer. Because in theory, what you could do, and I don't think that you should do it, is you can get the stack pointer, and then you can go back from a stack pointer and then get the pointer to the field data array inside of MPI wait, and then overwrite the field data array, meaning overwrite the function pointer that is called later. Yeah, whoever does this probably deserves to go to hell. But so we need to tell the compiler that actually MPI developers are quite nice people. They don't come straight out of hell. So they will not do these kind of, let's call them programming practices. Because if you do this correctly, whatever correctly means in that case, this is not undefined behavior. So the compiler actually needs to make sure that everything works correctly if you do that kind of stuff. But if we tell the compiler that actually MPI wait behaves quite nicely, it will only access this memory either directly through the pointer argument or some internal memory of the MPI library that we don't need to care about. Then the compiler knows, I see, the field data can now not be changed by MPI wait anymore. And then what the compiler sees, okay, I know which member of field data is loaded here, so I know the pointer, and I can figure out to which exact function, member function, the call needs to go. And then you replace the indirect pointer call, the indirect function call through the pointer here, can replace it with a direct call. Unfortunately, this only happens for the first iteration of the loop here, because the function that is then going to be called has exactly the same problem. It is defined in a different translation unit, the member function of the object here, and then it triggers the exact same problem. But for the first iteration, just by using the MPI, just by annotating that MPI wait behaves quite nicely, and don't mess around with your current stack pointer, the compiler is able to replace an indirect call with a direct one. In this case, actually, it removes a lot of instructions. Most of instructions are not necessary in the first place. They are needed to deal with the possibility of some virtual calls. Yeah, so the amount of instructions that we see in the binary in this case actually decreases by a lot, because the compiler can replace a lot of instruction necessary to deal with this indirect call by just plugging in the direct call here. I hope it was somewhat understandable what this does here. It is a bit more esoteric examples, because usually in code you see that the member functions are used directly and not indirectly through an array of pointers to the member function. So some other, yeah, now more relevant or more often seen case is conditional hoisting. Again, the relevant attribute here is for the MPI com rank. And especially relevant the annotation that my PE in this case, the variable will not change anymore. MPI library will forget about the variable. It will not override the variable later on. Here, what happens without the attributes is, okay, we need to evaluate the condition. So we first need to load the current rank from memory, and then we need to evaluate the condition. And here in the loop, again, we need to first load the value from memory because maybe the MPI library has changed the value in between. We need to make sure that we are using the correct value. And then we again need to evaluate the condition and so on. If you tell the compiler, though, that actually we only set MPI, my PE in this case, the rank only set it once, and then the MPI library will not override the rank because the rank of the current process does not change, then the compiler sees, okay, this conditional, this conditional, this conditional, if this conditional evaluates to true, or the other conditionals will also evaluate to true, so you can perform some condition hoisting, meaning that you only evaluate the condition once, and then you jump into a code with either all the print statements, in this case enabled for rank 0, or without all of those print statements for the other ranks. In this case, this means that a lot of code is duplicated, so that if you have a look at the general binary, the size of the binary can increase in this case, because basically all the code here is duplicated, but the amount of instructions that we need to execute during runtime will actually decrease because we only need to evaluate the condition once and not every time. In addition to saving the evaluation of the condition, what we also save is the memory access every time. Because we do not need to access the memory in order to load the myPE variable back from memory again. And again, the relevant attribute here is the no capture attribute, because we need to tell the compiler that actually the MPI library will not modify my process anymore. Some other examples where we can reduce the number of unnecessary memory accesses here, for example, with an all reduce operation, we see that first the variable is reduced locally and then it is reduced globally over all processes. What the compiler then generates is, okay, we unroll the loop here, nice, and then we perform the addition, and then we need to store the value to N1 again, and we perform the next addition, store the value again, perform the next addition, store the value again. And so on, because maybe MPI library has kept track of N1, maybe it has the pointer of N1 and it is querying the pointer over and over again in order to like do some event if N1 gets larger than 10, whatever. In this case, so the compiler needs to write back into memory again every time the value of N1, because maybe the MPI library is reading that value in between. Again, the relevant attributes here is in this case for the message buffer, that the message buffer is not captured, so that during the all reduce operation, during the all reduce operation, MPI library will read the value, but after the all reduce operation, MPI library will forget about the value. There is no like other thread in the background that could access the variable anymore. So we don't actually need to like write it to memory every time after we've performed the addition. And this is what happens here. If you perform the no capture attribute, you get this kind of assembly code where you see, okay, here the operation, the addition takes place in register, and it is not written to memory after every loop iteration, only at the end after the reduction has completed. Then we need to write it into memory so that the MPI library can then read it from memory in order to transfer it into the other process. In this case, we also see that loop unrolling is not done by the compiler anymore. The attributes do not prevent loop unrolling in any way. I suspect what the compiler sees is that here, between this move operation and this add operation, instruction level parallelism can be used in order to overlap those. And here, I guess the possibility for this kind of instruction level parallelism and overlapping some operations is not as high anymore, so that the compiler decides that, okay, loop unrolling in this case may not be worth it. Yeah, but of course it depends on what the exact heuristics are that the compiler is using in order to decide if this kind of unrolling is worth it or not. But we do see that unnecessary memory accesses are reduced. Question is, what is the impact on performance? On the mini apps that we tested, there is no measurable difference on performance. The reason here is that the optimization mainly occurs where MPI is used. And for example, if we do this conditional here, sure, we save a couple of memory accesses, couple of condition evaluation, but the actual important part, the calculation that is here and takes up most of the runtime, is not influenced here. Yeah, because usually what you want to do is you don't want to use MPI inside of your compute, have a heavy kernel of your application anyway. So MPI mostly is used in the management code around the kernel that manages how to execute your application across several different processes. So the optimizations also happen in this kind of management code, and therefore the runtime effect is limited, meaning that we cannot measure for the mini apps any performance difference. We basically measure the same performance. We can show the general effectiveness of those kind of operations with, for example, some more synthetic examples. If we do something like this, where the computation is not as expensive anymore, so that the evaluation of this condition is expensive, we can showcase that there is a performance benefit, in this case 16%, yeah, which is the reason why the compiler elects to do this optimizations in the first place. So in conclusion, we see that annotating attributes to the MPI function in order to tell the compiler more about the memory access semantics of the function influences code generation. There are several additional optimizations that are possible, and they may have different impact on different applications. Currently, we don't see any performance benefit in the analyzed applications. But we do think that the usage of those kind of attributes is generally sensible, because they can only improve the code. There is a reason why the compiler performs this optimization in the first place, and it does not introduce any additional overhead in terms of compiler analysis, because the compiler performs all of those analysis anyway and then figures out, okay, the optimization is not applicable, and now the optimization is applicable. Also, it is worth to note that the only thing that we have done is basically we've tell the compiler relevant attributes for the MPI library. And this approach would work with all standard compliant MPI libraries, because it's not specific to one specific library. And also, we do not include any extra kind of compiler analysis that is necessary or any other optimizations. The optimization that I've showcased, they are already part of the LLVM infrastructure, and the usage of those arguments, the attributes themselves, they are also already part of the LLVM infrastructure. So we are just using the already well-established parts of the LLVM infrastructure in order to trigger some compiler optimization that were there in the first place, and they are there for a reason. So it also does not introduce a lot of tool chain complexity overhead, in terms of that you need to use some research code in order to have the proper attributes. You can just use the well-established attributes and then hopefully get a better performance out of your application and give your compiler a bit more chances for optimizing the code here. And with this, I want to thank you for your attention, and I'm looking forward to have an interesting discussion with you.
Yeah, so thank you very much for this interesting talk. I see already the first question.
You added, I think, some attributes to the ISEND with the read only, I think, and no capture. I think that is actually wrong. And you say that it's because accessing after the completion is undefined behavior due to because of the standard, right?
Yeah. So
the compiler doesn't read the standard.
If you only see the MPI ISEND, this is wrong. Okay. But if you see the MPI ISEND in whatever else is happening here, this is correct in terms of that. What the no capture basically is telling the compiler that MPI will stop using the memory after the function call has completed or after the operation has completed. And then the key thing here is that we know from the MPI standard semantics that the user application code is not allowed to access the buffer while the operation is in progress. So the user first need to ensure completion before accessing the message buffer again. And in this case, we assume that the user ensures completion. In this case, telling the compiler that actually MPI is done using that memory is correct because the user has ensured completion, and after completion, the memory is not used anymore by him.
The user has ensured that, but the compiler needs to continue ensuring that throughout the pipeline. If you don't give the compiler the information that it will capture, then it can't. Because, for example, if you have allocation of memory, you ISEND it, or you fill it up, you ISEND it, then you iWait on it, and then you free the memory. If you have those attributes, I think the compiler is actually free to move the allocation of the memory between the receive and the weight?
Yeah, that of course depends on what exactly the attributes for the weight function are.
Right.
Because the attributes for the weight function, we try to like, what do you say, more loose attributes, so that more strict attributes in that sense that the compiler is not allowed to move anything past the weight function, because you need to, in this case, of course, treat the weight function or the other completion function for that matter as a sort of memory fence where you are not allowed to move function calls around.
Okay, then that would make sense. Thank you.
So following up on it, what is the benefit of putting no capture there? Why not add the capture for the?
If you're doing this with an MPI or reduce here, in this case, if you put no capture in here, you save the memory accesses here. If you don't put no capture in here, you will need this memory access.
Sure, but in this case, the pointer is not captured. In the case of ISINT, it is actually captured.
Yeah, exactly. So the key thing here is if you use an I/OR reduce in that stat, and here let's assume a different, not N1, but a different memory gets accessed, and then you ensure completion before the next iteration of this do loop here. In this case, what will happen is that if you say, oh, MPI I/OR reduce captures the pointer, then MPI, the compiler, does not know that after the loop iteration has finished and you have ensured completion, the compiler still assumes that, okay, this memory is captured by MPI. Whenever I modify that memory, I need to write to that memory directly inside of the next loop iteration. Yeah, so the compiler then assumes, okay, it's too much, so to speak. So the compiler needs to be extra sure. If we tell the compiler, okay, actually it commences right here or at the next point where you ensure completion, because we know that in between here, where only different memories are accessed before completion is ensured at the end of the loop, user is not allowed, user will not access that. If the user accessed that, it would be undefined behavior in the first place. Then after the loop, the compiler sees for the next loop iteration, okay, all reduce has not captured the pointer, I can remove those memory accesses here.
Okay. If I can, I have another question. So you're making assumptions about MPI calls that are not codified in the standard. You're assuming that we're not doing things in some MPI, like MPI comrank, right? And that allows the compiler to hoist it out of a loop.
But are there anything of this assumption not codified in the MPI standard? Like, is a standard compliant MPI implementation allowed to capture the pointer and then modify whatever is in the variable after the call? I don't.
No, it's not. It's not
the standard.
That's not my question. That was just a statement of fact. My question was, do we need more guarantees in the standard? Would that help if we codified more of the behavior of the API into the document to give you more guarantees for this work?
Yeah, so I think what is currently in the document was enough in order to derive this kind of attributes here. I'm not sure if the MPI standard should actually tell that this is no capture, because this is like technically wrong. And I think if you do something like that, there will be much question about that. In general, I think it may be a good idea to, for example, for this kind of management function, MPI get comrank, to tell, okay, this is a no capture function. Yeah, because on some level you can use this in order to make the semantics more clear, and especially important, the compiler can perform some optimizations there that it otherwise is not able to perform here. But I think you need to be careful what kind of attribution you want to have in the standard document, because I think those kind of attributions here, yeah, we also had the discussion about that, if this is actually correct or not. So for those kind of more complicated involved cases than the straight up cases with the MPI comrank, I think maybe yeah, it's more important to focus on the more straight cases there.
Yeah. Okay, so one comment here, for example, right? Sorry, if I may, interrupt me if I'm. So here, the data type and the communicator in the new ABI, it is a pointer. right? And we can probably define that we won't change the data type. It's not const in the API because it's not a pointer in the API, but in the ABI it's a pointer. So those things I think I like this work, and I think we should think about it now. Thank you.
One short thing, because it came up in a chat show. Jeff Hammond just mentioned that for the iSend problem we had before, the standard was changed recently. So for read operations, it was fixed more or less, so you don't have the issue. Okay.
I was wondering, are the attributes that you can use here rich enough to capture all the semantics that would be useful for optimization? For example, the no capture being a bit of a fudge in terms of the semantics already in terms of the LLVM notations. Is it worth pursuing an expansion of these attributes within, say, something like LLVM?
Yeah, I'm not entirely sure about that. The key thing here is that I guess there is a reason why LLVM uses this set of attributes and not other attributes. Some of the reason may be that usually, so here we derive that by hand, but usually the compiler will derive these kind of attributes by itself and then use it for interprocedural optimization. This is why we have those kind of attributes in the first place. So I'm not entirely sure if it is a good idea to just for MPI get some new attributes into the compilers, because in order for the compiler, for the LLVM people, basically, I think to pick up on this sort of very new attributes, then I think it is a good idea if this is not only a use case for MPI, but also for some other interprocedural optimization that can be done.
Of examples of other sorts of asynchrony where you would like similar guarantees, like for this period, it's owned by someone else, bring it back. So, you know, but maybe there are other opportunities.
So I just wanted a question/comment following up on what Josef said before. What can we do from the standard to help this work? And we currently already have kind of an initiative in there to make things more machine readable and to actually have semantics exposed in an automatic way. And certain parameters, the behavior of that is already specified and could be basically extracted automatically, which may help you perhaps automatically generate those attributes without even having to go through a manual thing. And so I think it would be interesting to see what else we could add to this automatic procedure to help you get this. Perhaps it doesn't have to say no capture, but it has to be another way to convey the semantics where you can extract those things from. So it'd be interesting to hear your thoughts on what we should add, or what information would you need from us and the standards part to make this work more automatic?
Yeah, I guess like maybe something like no capture or in this direction would be very helpful. I'm not entirely sure how other compilers are handling this, because like the no capture term for LLVM is specific for LLVM and has a defined meaning in the LLVM space. Maybe the GCC people call it differently and they call this no escape. I'm not sure how they do it. And I think what will be very interesting is to think about, okay, how can we manage that so that different compilers can use the standard and that different compilers can compile MPI programs and the different compilers can unlock those optimization potentials there. Yeah, but I guess some form of, okay, like put in something like read only or write only and no capture is, I think, pretty clear and should work with compilers. Maybe the key thing here is how can we, and I'm not sure how to do it, how can we present the information in a way that basically all the compilers can use the information, or at least ignore the information if they don't want the information here.
Okay.